class, I wanted to start this section. This is section 1.1, Systems of Linear Equations, and you have probably covered this in college algebra, I would think, or somewhere. So a system of equations, just two, in this example, it's two equations and two variables. And when we solve a system like this, we're finding the ordered pair x1, x2 that works in both of these equations. So we can solve this system using elimination. We could also solve it using substitution. Those are two methods that are taught in college algebra. So in this course, we're going to think more about elimination, because when we work with matrices, it's more like the process of elimination. So if this system of equations has a solution, that solution is actually the point of intersection of the two lines that are represented by those two equations. So in this case, I believe these are the two lines, and that is the point of intersection right there. I graphed this, I think, with GeoGebra, which we'll talk about some later. So there's three things that can happen when you have a system of equations. It may be that it has no solution, like if you're talking about lines and there's no solution, that means the two lines are parallel. It could have exactly one solution, and that's like where we saw just above, where there is a point of intersection and exactly one point of intersection. Or there could be infinitely many solutions, and that happens when the two equations actually represent the same line. Now, if you have at least one solution, then the system is said to be consistent. So if it has either one or it has infinitely many solutions. And if there's no solution, it's called inconsistent. Now, when we get to bigger systems, we're probably going to want to use a matrix, and that's what this course is about. Linear algebra is about the study of matrices. So, for example, if I have a system like this, so this is a system of three equations and three variables. So if we have three variables, we probably need three equations. And it doesn't matter that, like in this equation, there's only two variables. There are three variables if you look at the system as a whole. So the way you would write this out is a matrix, and this is where I entered it into my calculator. You have to tell the dimensions, and the dimension of the matrix is the number of rows. So in this case, it has 3 rows times the number of columns, and it has 1, 2, 3, 4 columns, or it will have. This is what we call an augmented matrix, because it has the last column is what really the constant terms over here. These numbers are constant. Now you want to be sure you enter it in the right order, so you want all of your x1 terms first, then your x2 terms, then your x3 terms, and the last column should be what it's equal to right here. So we enter those coefficients, and this is called a coefficient matrix, because if you look right here, we're just entering the coefficients of these variables. And so we enter them into our calculator, and I'll show you how to do that in a minute. And then this just says that it's an augmented matrix, and then it tells a little bit more over here about the matrix size, which I just told you. So it's the number of rows times the number of columns. And now to solve a matrix, the basic strategy is to replace one system with an equivalent system, which means it has the same solution set that is easier to solve. So what we're going to do are elementary row operations until we get the matrix in a form where we can read off the solution set, or we can use back substitution to solve the matrix. So the things we can do is we can always replace one row by the sum of itself and a multiple of another row. We can interchange two rows, and we can multiply all entries in a row by a non-zero constant, which means also we could divide by a non-zero constant. And two matrices are called row equivalent if there is a sequence of elementary row operations that transform one matrix into the other. Now, this is example 1. We're going to solve this matrix. So, basically, we want to use the x1 term in the first equation to eliminate the x1 terms in the other equation. Then we're going to use the x2 term to eliminate this x2. So basically we're going to get zeros here below this x1, zeros here above and below this x2, and then we'll use the x3 term to eliminate these two. And then what we'll have is we'll have a matrix where we can just read off the solution set. Now this is actually with using the equations right here. But we're going to use a matrix. This is just the answer from the back of the book. Let me go over to where I worked it out, and I'm sorry this is not just real neat, but this was a system of equations, and then I write out the matrix. You want to be sure you get that correct. And then what I'm going to do, because I want to eliminate right here. So I'm trying to eliminate this element right here. So what I'm going to do is I'm going to multiply row 1 times a negative 2. I'm going to add it to row 2, and that's going to be my new row 2. So when I do this and I multiply row 1 times negative 2, I get negative 2, 0, a 6, and a negative 16. And then I'm adding that to row 2. And this is what I get when I add them. So this is my new row 2. Now, go back to this. What I want to do after that, and let me get rid of that, is I want to get rid of or eliminate this right here. This is what I want to eliminate now. So I'm going to take, actually what I did here, instead of doing that, I didn't eliminate that right here, and I could have. What I did, since this is a 1 and this is a 2, and I'm going to want a 1 right here in this position anyways, I just interchanged row 2 and 3, and then I worked with that. So you can always interchange rows, so I just interchanged row 2 and I interchanged row 3 with row 3. And then I want to eliminate, this right here, okay? So what I'm going to do is I'm going to multiply row 2 by a negative 2. This is row 2. I'm going to multiply it times a negative 2, and then I'm going to add it to row 3, and that's going to be my new row 3. So I have a 0, a negative 2, a 10, and a 4, and I add it to this row, and this is what I get, and this is going to be my new row 3. So I just write that in. Now I can go ahead, since this might make it just look nicer, I could divide row 3 by 5, and I have this. So notice that what I have right here is a triangle of zeros. So that's the idea, is to get a little triangle of zeros right here. Once I do that, it's in what's called echelon form, and I could solve the matrix. I could do some more row operations, and I could get rid of all of this right here. And so that I just have ones down the main diagonal and some numbers right here. So I would be getting rid of this and this and this, I think. So, but I could do that. I could do more row operations, or I could at this point use back substitution. And that's what I did here. Because remember, these were the coefficients for x1, these were the coefficients for x2, these were the coefficients for x3, and then it said equal in each equation. So this line right here means, so if I look at this line right here, this line means 1x3 equals a negative 1. And so that means that x3 is equal to negative 1. This line right here means that x2 plus 5 times x3 equals negative 2, but I know x3 is negative 1. So I can substitute in the negative 1 and solve for x2. And then I didn't actually do it, but I can go back and I can substitute in for x3 and x2. And actually there isn't an x2 value here. So all I'd have to do is substitute in for x3 and I could figure out what x1 is. But I didn't show that on here. So now let's go back to our other page. This is where they did it, and when the little squiggly lines mean that it's equivalent. And now what they did was they went ahead and they reduced it to reduced row echelon form, which is where you've got zeros here and you've got zeros in this little triangle right here. Then what this means is x1 equals 5, x2 equals 3, and x3 equals negative 1. So that's the solution set. Now it's an ordered triple, and if it's an ordered triple, the equations determine a plane in three-dimensional space. The three equations, each one represents a plane, and this is the point where that lies in all three planes. Okay. Now, two fundamental questions about a linear system. Is the system consistent? Like we just found out whether that particular system was consistent, and it was. So that means does at least one solution exist? And then if the system is consistent, is there only one solution? That is the solution unique? So there's an existence question and there's a unique question that we talk about a lot in this class. Now here's example 2. So we have a system of three equations and three variables. This is where they did it, and let me go over here and show you where I did it, which is not necessarily too neat right here, but this is example 2. I wrote out my matrix, and then I looked at it, and if I multiply row 1 times a negative 3 and add it to row 2, I'm going to eliminate this right here. This is the first thing I want to eliminate, is that. So that's what I do. I multiply row 1 times a negative 3, and then just add it to row 2, and this is what I get. Okay. Now, instead of rewriting my equation yet, I'm going to go ahead and do some more eliminating. So I've got this, and now what I want to eliminate is I want to eliminate this value right here. So to do that, I'm going to take 4 times row 1 plus row 3, because if I multiply this times 4, that'll give me a 4, and a 4 plus a negative 4 is 0, and that's going to be my new row 3. So I multiply row 1 times 4, and I get this, and then I add it to row 3, and then I get this. And then I went ahead and I wrote my new matrix. So my new matrix with the two different row operations that I did look like this. Now what I want to do is I want to eliminate this value right here. Okay. So what am I going to multiply row 2 by? Because I'm going to use this as the position to eliminate this. Well, I'm going to have to multiply it by a positive 3. That's a positive 3 right there. If I multiply row 2 by a positive 3 and add it to row 3, and that'll be my new row 3, this is going to end up being a 0. So let's do that. So I multiply row 2 times 3. Here we get row 2 multiplied times 3. I add it to row 3, and I get this. Now, I can stop right now because when I get this in any row, what it means, if you think about it, this means equals 3. So it's like 0 times x1 plus 0 times x2 plus 0 times x3 equal 3. Just think about the last position over here, if you think about this, this means that 0 times x3 equals 3. That's not possible. I mean, if you were to try to solve that for x3, you'd be dividing by 0, which is undefined. So what that means is this example has no solution. Okay, there is no solution. So this is where they did it from the book. So the system is inconsistent. So if the last row has zeros and then it has a non-zero right now, then that means that there is no solution. Okay, so the solution set is empty. Now here's another example. So let's look at this example. This is example 3. Let me go back up. Here it is. Sorry, this is kind of messy. So I write out my matrix, and I'm going to want to get rid of this value right here. So to do that, I'm going to multiply row 1 by -6 and add it to row 2, and that's going to be my new row 2. And I do that, and I get this for my new row 2, and I just went ahead and divided my new row 2 by -5. So this is my new row 2. Then the next thing I want to do is I want to use this to get rid of the 8. So I'm going to multiply row 1 by -8, and so I do that over here. I go -8 times row 1 plus row 3 is going to give me my new row 3, and then I get this for my new row 3. And then I divide, go ahead and divide row 3 by -7, because that will, -7 will go into all these values, and I get this for row 3. Then I could, the next the next position that I want to get rid of is actually this one. But to do that, I would end up adding or multiplying row 2 times -1 and multiply it times or add it to row 3. So if I do that, look at what happens when I do that. These are the whole row, every every position in the row here is the opposite of the positions here. So I get, when I do that, I get 0, 0, 0, 0 in the last row. What that means is that 0 times x3 equals 0. But 0 times any number will give me 0. So this is the example when there's infinitely many solutions. It is consistent. So x3 is what we call a free variable. And that was this last example that I actually had told y'all to try on your own. You might want to go try this at this point now without looking at what I did and see what you get. So I believe that's the end of this section. So I'm going to stop my recording for right now.